Hi, my name is Arjun Kaushik, and my research proposal for this summer was creating an unsupervised machine learning algorithm for user association in wireless networks. User association refers to the problem of assigning mobile users to base stations in an optimized manner. Parameters such as spectral efficiency, data rate, and power allocations are either optimized or maximized. Some methods of solving user association include brute force method, which provides a high complexity as we have to check every possible combination there is, and the complexity is of about n factorial. Another method is using the Hungarian algorithm, which gives a polynomial time complexity by finding maximum weight matchings for assignment problems, and it's able to represent our data into an adjacency matrix. And another idea for solving user association is using maximum SINR, where SINR is a signal to interference plus noise ratio. And we can use this if our input data is SINR. This provides a polynomial time complexity but does not allow for custom things such as constraints. And finally, researchers have been moving towards using machine learning to solve the user association problem, and in particular, supervised machine learning. And some examples are neural networks and reinforcement learning. But some issues with with these ideas is that it requires a known output when testing the machine learning algorithm, and it needs us to solve the optimization problem. And another issue with the previous mentioned methods is that in real life scenarios, data is being updated constantly, and using scenarios such as brute force, maximus NR, and Hungarian algorithm, it need to be computed every single time to get the optimal solution or user association values. Therefore, we're motivated to use unsupervised learning to solve user association. And some factors are that there's not much research that has been done using unsupervised machine learning. Unsupervised machine learning does not require solving the optimization problem. It does not require labels for our output data. It allows the use of unlabeled data, and it allows custom cost functions or loss functions which can be used. So moving on to our system model and problem formulation, we take a scenario of a heterogeneous network consisting of RF and terahertz base stations. We develop our SINR data using MATLAB by using the formulas to the right-hand side, where SINR is a SINR for the RF base stations, SINRT is a SINR for terahertz base stations, HFR is a line of sight channel power between user and the terahertz base station, and G is antenna gains. From there, we feed this data into a deep neural network to develop our user association values, and our main objective is to maximize user data rate. Continuing on to formulate our problem, we take set I, which is the set of our users, set J for the base stations. We use a Shannon's expression to write the data rate, and we then introduce our user association indicator, which is U, or UIJ, where I is the user and J is a base station. We can finally write our achievable data rate as the double summation of UIJ into RIJ, and our final problem is formulated as the maximum of R. Our problem is then subjected to three constraints, where C1 states that our UIJ is between 0 and 1. If it's 0, that means user I does not associate with base station J. 1, where user I does associate with base station J. The second constraint states that a user can only connect to up to one base station at a time. And the third constraint is the threshold of a base station of how many users it can handle. So the structure of our neural network is coded in Python using a TensorFlow backend. It consists of 4 hidden layers of one input and one output layer. Our input data is formed as I into J channels. The input layer and output layer consist of I into J neurons. ReLU is used as an activation function for hidden layers, while softmax is used for the output layer to produce the probabilities of our UIJs. For the training, we implement a custom cost function, which is C, and that is basically the negative of our achievable data rate, which is a double summation of UIJ into RIJ. Our initial scenario consists of 3 users and 4 base stations, which is our 12 channels. Our training set we take of 10,000 users, which is created through MATLAB. And by testing different batch sizes and learning rates, we saw a batch size of 128 and a learning rate of 0.00005 was the best one we took. So the results we got was we compared our prediction results from our neural network to the maximum SINR algorithm. We took 4 different test cases, and as we can see from this table, our neural network produces results which are very similar to maximum SINR, which is very good, and it shows that we are picking the correct hyperparameters, but they can still be further optimized. Our future steps include implementation of constraint 3 of the threshold of base stations as that has not been done yet. Further fine-tuning the neural network through the hyperparameters, including the number of neurons, the learning rate, and batch size. And finally, comparing the neural network results to traditional solutions such as Hungarian algorithm. Thank you for listening to my presentation, and I'll be open to any questions.